Hi there, everyone. Welcome to your week 3 lecture. I do need to apologize. First, I was not able to get this done before I left for the weekend, and so I'm having to do this from my house. And I'm a little embarrassed. I wanted to be in our first library. This is our second library, and it's fine, I guess, but the first library is much nicer and it's being cleaned. So hopefully this is okay. It's not too much of a distraction for you, hopefully. So I do apologize about that, but we'll get going here. And of course, we'll start with the chemistry cat joke. So I'm just going to go ahead and let you take that in. Great. All right, we have been talking about the history of the atom. We, together in breakout rooms, put together a document that ended with Rutherford. After Rutherford comes Bohr. Now, real quick before we get into the Bohr model, yeah, I will sometimes show you these slides that have this yellow background, and the intention is for you to pause and kind of think through and answer this question. There's no way for me to know if you do that or not, but I am putting these into the lectures for a reason, and so that's my kind of hint to you when it comes to upcoming quizzes or tests in terms of material that you're going to want to know. So here we're asking you to look at that image and talk about which scientist would have that model. And that's Thomson. Remember that both the Greeks and Dalton would have pictured a solid sphere, and that's not what we have here. We have components, right? They originally thought an indivisible solid sphere, and there are both positive and negative parts to this one, so it couldn't be Greek or the Greeks or the Dalton model. And it's not Rutherford, because Rutherford talked about a tiny little nucleus and the electrons existing in empty space around it, and that is not what's being depicted here. So as you think through kind of process of elimination, this would be Thomson's plum pudding model. Now, when I asked you to draw what you think an atom looks like, and again, not right or wrong, I just want to see where you're all at, but a majority of you gave me something that looked like this. Some of you gave me even a little more detail and gave me something that looked like this. And there's a reason that so many people, when they envision an atom, give the Bohr model. That's incorrect, although it's interesting. I will use the Bohr model to help illustrate things throughout the class. So obviously there's some, some correct parts to this model, but it's not quite the complete vision of what we now see an atom to be. And as I mentioned as well, like they use this everywhere. I think the Department of Energy has this or something similar as on their logo, even though it's not quite correct. So the idea is, how do we get here? How do we get to the Bohr model? And how are we going to then move on to our kind of final vision of the model of an atom? So it starts with Planck. And what he proposes is that very specific amounts of energy are being associated with an atom, and we call those quanta of energy. And so early on, he saw that. A little bit later, Bohr kind of ran with that idea, and he specifically said that electrons can possess only certain amounts of energy, quanta of energy, and that therefore they can only be existing at certain distance from the nucleus. And so his is called the planetary model, and I will show you why that's the case, but I think you can kind of picture it already. And again, what he's saying is, if we have that atom right there, so the nucleus is going to be in the middle here, so we have protons and neutrons in the nucleus. Here's one energy level, and here's a second energy level that electrons could exist. They're at very specific distances. So again, it's circular in order to maintain that specific distance. And what he's saying is an electron can exist at this distance or at this distance, but not in between. And that's a little bit of a weird idea, and it'll take us into next week, really, to kind of wrap our heads around what that quanta idea means and how can an electron just exist here and then all of a sudden exist here. So that's what we'll talk about through the last model next week. But this is the planetary model. So getting back to this idea of these quanta of energy, you have that chart on the left. I actually think a better analogy is this. So if you were to think about kind of walking up this ramp, you could exist at any point continuously along this. Now compare that to steps. You have to exist on this step or this step. You can't be hovering in between those two steps. And that's what we mean when we talk about electrons existing at very specific amounts of energy and very specific distances from the nucleus, again, according to the Bohr model. And we will work through that model and improve it into next week. So this is what we mean by continuous energy versus these quanta of energy. So here's that final look at the model, Bohr's model. So you have the nucleus still that is coming from Rutherford. We've got the electrons, again, still existing in this empty space around the nucleus. But the idea is that there's specific orbits and energy levels in which these electrons will exist. They need to possess a very specific amount of energy in order to do that. And again, this is why it's called the planetary model. But what we will realize is that electrons really don't behave like planets where they orbit in a specific path. So we need to get that out of our head. So they don't orbit, even though we are going to continue to call these orbitals as we talk through how electrons reside around an atom. So then what was his evidence to come up with this model? And it comes down to light. So you will see that in our lab this week, we're going to involve light in different colors, whether you're doing the in-person or online version. And so that's what he was working with. And specifically, it was these emission line spectrum is what he was seeing. And I'm going to assume that a number of you have been exposed to this type of thing, especially in earth science or astronomy. But what you see is that for each element, we're getting unique spectra being formed as these emission lines form. And the idea that he was coming up with here is that it must be because of those very specific amounts of energy electrons possess, they must be able to put off these specific emission spectra. And so we'll get into that over the next few slides. But this is what he was seeing that eventually led him to that conclusion. So before we kind of come back to those spectrum, let's just talk about light in general. And so there's a couple of slides worth of notes here, but this is what you need to be using when we ask you to explain what's happening in our flame test lab. So to start, if we have an electron in its lowest possible energy state, and that means all the electron, depending on which atom we're dealing with, when they're in their lowest possible energy, this is called the ground state. It's kind of like the ground floor almost. Now, it doesn't mean that every single electron is right next to the nucleus. We will learn that really there's specific numbers of electrons that exist in different orbitals. But for now, it just means that all of the electrons are in their lowest possible energy. So let's say helium as an example. So we'll have two electrons and they'll both be residing in that closest energy level to the nucleus. Now, if one of those electrons or multiple electrons absorb a specific amount of energy, so the right amount of energy, they can move up to a higher energy level. So as we move away from the nucleus, those energy levels have higher and higher amounts of energy associated with them, meaning that that electron would need to absorb energy in order to move up. Now, that situation, which we call the excited state, is unstable. So an atom wants to be stable. It wants all electrons in the ground state. But if we force energy upon one of those electrons, it'll move up if it's the right amount. But as soon as it can, it wants to move back down to ground state. So you'll notice here energy, we're going to be using heat in our lab, but you could talk about light or electricity as a form of energy. So you'll notice that when that electron absorbs that energy, it moves up. Again, it's unstable. It does not like being in that configuration with extra energy. But because it absorbed that right amount of energy, it moves up. And again, when you think about this, again, it absorbed the energy and it had to be a very specific amount to then exist in that higher energy level. There was no in between. So the electron was either in that first energy level, all of a sudden it absorbed enough energy and it's then existing in the second energy level. So it's not continuous. Even though I'm going to draw lines where I'm saying, oh, it moves from here to here, that's not a great way of showing it. It's hard to show it differently. So be careful of the continuous versus the quanta of energy. So now you'll notice that we've got one electron in its ground state still, but the other electron is in this excited state. So as I've been implying, that electron and the atom in general does not like having extra energy associated with its electrons. And you do need to be careful. I hear a lot of times students saying that the atom moves to an excited state. It's the electrons around the nucleus that are moving to an excited state. So we're going to get that electron to fall back down. But because it absorbed energy to exist in that higher energy level, it's not going to be allowed down into a lower energy level. So for example, because this electron has more energy associated with it, it's not allowed down in this energy level until it releases that energy that it originally absorbed. So that's where we get those emission line spectra. And that's where, as you start to do the lab, you'll see this is where we get some of the cool colors that you see. So yes, the electron wants to move back down to its ground state, but it has to release that energy first. And in this case, it's going to be in the form of photons and light. So now, because it released that energy, it's allowed back down into the ground state. And then if it were to absorb energy again, it would move back up to an excited state. Again, it has to be the right amount of energy. So when we talk about the right amount of energy being released, those are those lines on the spectra that we'll come back to here in just a moment. Actually, right now. So again, each of those lines represents a very specific fall for an electron. We showed you just moving from first energy to second energy level and back down. But really, the energy levels around an atom go on for infinite. Now, of course, at some point, if enough energy is added to an electron, it just goes away, and we get an ion forming. But even within the energy levels, there's a lot of potential moves, a lot of potential absorptions and releases that can happen. So that's why we get multiple lines. So again, the simplest little animation I can do here is there's an electron in a ground state. It's going to absorb energy. It moves to an excited state. That's unstable. It wants to move back down, but it has to release the energy first. As soon as it releases that right amount of energy, it's going to move back down to ground state. And if that energy is within the visible light spectrum, we will see a line in our emission spectrum. So if you were to just look at a light source right now, somewhere around wherever you are, the light coming from that source is just an electron doing that, well, many, many electrons doing this over and over and over. So again, coming back here, we've got hydrogen being excited, so that's going to be utilizing electricity. And what we can do is we can send that light through either a prism or a diffraction gradient, but we're pretty much going to split that light. The reason it splits is because the photons have differing amounts of energy because they have differing amounts of, or differing wavelengths. And so because it takes a little bit longer for some of those light sources to move through, that's why we get the splitting of those spectrum. And so again, there's the hydrogen, and why the multiple lines? So again, as I was alluding to previously, if we've got hydrogen here, there's the nucleus, so 1 proton, maybe 1 neutron, but likely not. Let's just draw some random energy levels here. Again, these would each exist with very specific amounts of energy and very specific distances from that nucleus. So let's say I've got an electron, since it's ground state, and again, it would not, I'm going to draw a line. It's not continuous like that. Ultimately, if it absorbed energy, it would exist up here. So again, it absorbed energy until it was able to move further away from the nucleus. And then when it moves back down, it's going to move from the second to the first energy level, and it's going to release a specific amount of energy. And maybe that's this line. So every time an electron moves from first to second back down, we get that line. Notice that instead, maybe this electron could absorb a differing amount of energy where it's allowed to move all the way up to this third energy level and then fall all the way back down to the first. And that might represent this line. So again, because you have unique combinations of those electrons moving up and down and releasing those specific amounts of energy, we get differing lines on the spectra. So that's why you get those multiple lines. And again, I'm not going to spend too much time here. I did want to point out, and it's going to be important for your lab, is that as I move from violet up towards red on this spectrum, that we're actually decreasing energy. The other way to think about it, and again, this is just, it's a little bit confusing, but the smaller the wavelength, the greater the energy. So violet is going to be the most energetic photon that you'll be seeing that's reaching your eyes, whereas red is the least energetic. So there's a question on the lab that you'll need to utilize something like this. And again, we can look at a bunch of different spectra. Each is unique. And when you see the overall color from each of these, you're just seeing the overall combination of those different lines. And again, we can figure out exactly on this wavelength where the color is falling and how energetic those photons are. So this maybe puts in perspective if you're a classic rock fan, this famous album cover. You might realize that white light is actually just a combination of all of the wavelengths of light. So let's quickly just double check in Bohr's model of the atom. Electrons in the energy level closest to the nucleus would have blank energy compared to the electrons further away. And again, in this case, it's lower amount of energy the closer to the nucleus. And again, remember that the electrons have to absorb energy in order to move further away and exist in a higher energy level. one more analogy here, just this idea of quanta and the spectrum lines that you see. It's kind of like maybe like floors in a hotel. And so you can be on the first floor, the second floor, the third floor. You don't exist in between. So that's the same idea as that's happening up here, because they have very specific amounts of energy required to move into each of these different energy levels. We get very specific, unique lines on the spectrum. Finally, here's the visible light spectrum, which we've been talking about, and you just saw from violet all the way to red. There's other potential jumps that are happening here. So notice that here you've got a jump that possibly all the way from the 6th energy level all the way down to the 1st. That's very energetic. That is a lot of energy being released. And that is actually ultraviolet radiation. So obviously we get a lot of ultraviolet radiation from the sun. So there's a lot of energy associated with a star, and all of that energy, having electrons move way up and fall way down, gives us UV radiation, but that's not visible to us. And so while you are going to have atoms giving off ultraviolet, you would not realize that. Those don't fall into the spectrum and they don't form a line. On the other end of things, you have infrared. This is mostly just heat. But again, atoms have the ability with smaller jumps, with less energy, to give off infrared radiation. So your visible light spectrum falls in between ultraviolet and infrared. And again, we can't see UV, we can't see the IR infrared. So we're only seeing the jumps that are causing visible light. One more check. And again, you got to be careful here. It is a specific amount of energy that must be absorbed. So not just any random amount. It's got to be a very specific amount of energy that allows that electron to move up into higher energy levels. Almost like a lock and key. You have to have the key, which is the correct amount of energy, in order to undo the lock and get into a specific energy level. Here's just a quick animation if you want to play around with it. If you're a visual person, this might help explain some of the things that are going on. And I just wanted to end real quick here with a connection to fireworks. So when fireworks are being made, they are being packed with very specific compounds based on the spectrum that those compounds give out. So you'll see in your lab that we're going to be dealing with some of these metals, but these metals and their electrons give off very specific and unique colors because of their unique electron jumps within their configurations. And so you know, those people making fireworks can have very specific shows in terms of the colors that they want. It all has to do with chemistry. Okay, so that is your week 3 lecture. If you are an honor student, you're going to have an extra lecture after this. But for the rest of you, this is it. So again, just understanding the Bohr model and how that relates to light is the biggest thing from this. Thank you for sitting through this. I appreciate your attention. Until next time. Hi there, honor students. You're getting some bonus material this week. And it's going to revolve around electromagnetic radiation, specifically photons. We're going to calculate energy for those photons. So that's the extension here. Still hanging out in the second library. The first one's still not clean. But anyway, again, it's embarrassing. But all right, let's talk about the electromagnetic spectrum here. I think at some point you have probably been exposed to this. And we've been focusing in on this visible light part right here. Now, the interesting thing about all of these, whether it's radio waves down here or something like gamma rays that are given off, you know, because of nuclear decay and things like that, and gamma rays are extremely dangerous to humans. But all of these are actually just photons. And so really, when you think about it, radio waves are actually just really slow moving light waves. And gamma rays are just really, really fast and energetic light waves. So kind of an interesting thing to think about. So if all of these are moving at the speed of light, then how do we get different energies? So we need to talk characteristics of a wave. You do not need to memorize any of these, but I will refer to them. And so I think it helps visually, just real quick. Crest and trough, don't need to really worry too much about. You will be utilizing wavelength, which is the distance between 2 points. So this could be, you know, the distance between this crest and this crest would be the wavelength. The wavelength is going to factor into the amount of energy associated with a wave. We have something called amplitude. We're not going to worry about that. But we also are worried about frequency. So frequency is the number of cycles, usually per time, so a second. And so the higher the frequency, the greater number of cycles are going to pass through a given point per second. So we'll be using hertz, which is going to utilize seconds. So wavelength and frequency are going to be used. So then how does this work out? So again, we're going to show you a photon to start, a single photon, moving through this wave, which has low frequency and a long wavelength. So this would be kind of like a radio wave. This photon is going to move through, but this time it's high frequency, short wavelength. And again, amplitude is the same here. And so really all we're going to change is the frequency and the wavelength. And you'll see, even though they're moving at the same speed, we're going to have a different amount of energy associated with them. So go ahead and watch as they move through the wave. So again, same speed. They arrived at the end at the same time, or almost as best I could animate. But you'll notice that that photon below in the high frequency short wavelength ended up moving much more. And ultimately what would happen is you can pack more photons into high frequency and short wavelength. So if you consider that versus that, there's more energy associated with the bottom one. And again, that has to do with number of photons that can move through that wave. And so ultimately, if you look at the top one versus the bottom one, we have low energy associated with the top, you have high energy associated with the bottom. So again, moving at the speed of light, but different energy because of frequency and because of wavelength. Okay, so then coming back to the spectrum here, you have increasing wavelength. And again, like if you look at something like radio waves from crest to crest, you know, their wavelength can be, you know, 100 meters up to. So a lot of times your radio waves are like the size of a house, the wavelength. Whereas when you come down here, these gamma rays, I mean, we're getting down towards the size of atoms and molecules. And that's why gamma rays are so dangerous, very energetic, and they're so small that they have the ability to disrupt atoms and molecules, potentially your DNA and things like that. As we move this way, greater frequency. So again, if you think about frequency as gamma rays come through extremely quick cycles through per second. Radio waves are kind of long and meandering. And that means that as I move from left to right, we're increasing energy. And focus in on this as well. If you look here, as I move from red to violet, we have an increase in energy. Okay, you will see these nanometers. It's going to be wavelength. And so we're going to utilize those. I was going to talk about how microwaves work. We'll talk about that in a different lecture. All right, so then let's get to it. How are we going to do these calculations? How are we going to calculate for the energy of photons that you see in your flame test lab? Well, we'll start with Nicholson, who is the first to calculate the speed of light accurately in a vacuum. And that number is 3 times 10 to the 8th meters per second, extremely fast when you think about a second, and then 3 times 10 to the 8th meters over that second. And we're going to actually put this into an equation which relates the speed of light to frequency and wavelength. So the speed of light is equivalent to the frequency multiplied by the wavelength. So a very useful little equation there that we'll utilize. And I should mention frequency. We're going to use F as our frequency. But you will sometimes see this kind of Greek V. And I think that's more of a physics thing when we talk about frequency. We in chemistry will use the F. But if you were to look online for help, you see a V, they're trying to tell you frequency. It's one of those annoying little quirks with chemistry versus physics. So then we talked about Planck before. I did not have a general class write this down, but you may want to realize that Planck dealt with quanta, and that's what we're measuring as the energy of quanta. So he's related and important there. And Einstein also was involved with this idea. He actually coined the term photon and developed the equation that allows us to calculate energy of a single photon. So again, I know I'm moving quickly. You can pause this, obviously, as you need. So we'll be using this equation. Energy we'll be measuring in joules. And then Planck's constant here, you can see is a really small number, and it's joules per second, or joules times second. And so you're going to end up, because we're using hertz, which is the inverse of seconds, you'll see that we're going to cancel out units easily here. We're not too concerned about units. I'll mention them again later. We will be concerned about units. We don't want naked numbers. We're going to be classy individuals in this class, no naked numbers. But early on here, I think I'm more worried about getting you through the math. Which, speaking of, scientific notation. I'm assuming and hoping that you've seen this type of thing before. I'm very proud of my meme here. But the idea is we're going to need to utilize scientific notation when you talk about a number as small as Planck's. You don't want to have to write that out. You don't want to enter that in your calculator. So we need to use scientific notation. I don't know where you're all at with scientific notation. If you want to fast forward through this because you know what's going on, great. I'm not going to spend much time on it anyway, but the calculator work is where I'm mostly concerned. So scientific notation in general helps us express really big and really small numbers. It always takes the same form. You're going to have a number between 1 and 9.999 infinity. And you're going to have times 10 as a base and then an exponent. We're talking powers of 10 here with that base, right, times 10. So if you think about 800 as scientific notation, you're taking 8, your number between 1 and 9.99, times 10 times 10. And so as a scientific notation, it'd be 8 times 10 to the second. Same thing down here. You'll notice that you got your number between 1 and 9.99 right here. And ultimately, what we're doing here is if I start with the decimal here, so if you don't have a decimal, you can place one, because this is not changing the value of the number. But if I move this until I get a number between 1 and 10, and it makes no sense to move it this direction. Instead, if I move it once, twice, and then a third time, and I place my decimal there, I get 2.531. And because I moved it 3 times, it's 10 to the third. That's all this is. And again, I am assuming that you've seen this before. We can do the opposite. We can work with small numbers. And we'd be dividing by 10 in this case. And again, we're going to get an exponent, but this time it's negative. And I don't have a great way of remembering that. I'll show you one perhaps way that works on the next slide. So that's what's going on with scientific notation. It's powers of 10, and it's moving the decimal until we get a number between 1 and 10. So keep that in mind. Now that exponent, again, if it's a negative number, it's indicating a number small, below 1, less than 1. If you have a positive exponent, that is a number greater than 1. So if you would like to pause and try one of these or a couple of these, great. Otherwise, like I said, I don't want to spend too much time if you know how to do this in your board. Here, if I'm in scientific notation, here's my decimal. And I would want to move that decimal 5 times until I use up all the exponent here. Now again, one way to maybe remember is that like the negative sign's on the left-hand side of the exponent, and we're going to move this decimal left to make a small number. I'm going to move it to 5 times. So 1, 2, 3, 4, 5. There's the placement for my new decimal. Fill in zeros for the placeholders, and you get your answer. So again, I don't want to bore you with this. If you need more help, I will absolutely help you. But I think a lot of you probably have experience with this. We can do the opposite. We can start in our standard notation and go to scientific. And again, here, I don't see a decimal to start, so I'll place it here. Won't change the value. We'll move it 1, 2, 3, 4 times until we get a number between 1 and 10, or 1 and 9.999, and there's our answer. So I'll leave it at that. This is a really important number in chemistry. It's called Avogadro's number. It's a huge number. We'll talk about it, but you do not want to have to put that number in your calculator every time you use it. You'll be using it a ton. So again, how do we then use calculators with scientific notation? And this is the part that I worry about. You need to be using, if you've got a TI, at least one of these, you need to be using the second button and then hitting this little EE. So it's the comma, but you're after that EE. So that's what we have right here. Casio's, it tends to be an EXP button right here. And then on this version of a TI, the EE button's right here. You don't need to hit shift. Now, if you have a different calculator than one of these, we may need to look at that together and figure out what's going on. So I'm going to spend a moment just telling you how to put scientific notation into your calculator. And I'm spending this time, not to bore you, with the Bohr model. Bore you? Okay, not to bore you, but it is so frustrating and annoying if you set up everything correctly and all you do is a little calculator mistake and you get the wrong answer. It's really frustrating, so I want to avoid that with scientific notation. Here's how you type it in your calculator, if it's Avogadro's number. Don't do something like this. Don't do times 10e, you're actually adding an extra decimal move there. So that actually is times 10 to the 24 by doing it that way, which you don't want. Don't do whatever that is. Pretty much use the EE or EXP button. If you have your own way of doing things, you want to be a rebel, and fine, but I'm going to focus on the EE button, and if you're getting the wrong answer by doing it your own way, I'm not going to help you. So I would just use the EE button. You may want to try this real quick, pause and try this in your own calculator, see what you get. But if I were placing this correctly, we're going to use parentheses. It's never wrong to use parentheses. Sometimes you don't need them, but it's never wrong. And I would just always put parentheses around each of your scientific notation terms here. So parentheses, and then you put 1.2, the E button 5. That's it. Don't do times 10. Don't do anything weird, just E 5. Close parentheses, divide. We get parentheses again and again. Just do 2.8. Hit the E button, wherever that looks like for you, 19. And you should, if you're doing this correctly, get something like that. Now, be careful because the E is calculator talk. So I don't want this as your answer. I definitely don't want this. So this number is very different from what I actually want. What I actually want is scientific notation with your base and your exponent correctly shown. Again, this is a very different number here than here. So just remember the E means times 10, and I need you to actually go to the effort of converting the E calculator talk back into your notation there. And if you wanted to pause and practice one of these, just choose one of these, see what you get in your calculator, and make sure you're getting the correct answer. I think that would be a good idea. So there we go. So then let's bring this all back to the work that we'll actually be doing. You'll be using those two equations that I showed. And it depends on what you're solving for. You might need to use them both. Now, one of the confusing things I think for students sometimes at first is they forget that C is given to you. So speed of light always doesn't change meters per second. And that Planck's constant is always a number that you know. Because otherwise it's going to seem sometimes like I'm not giving you enough information. But I am if you remember that those two things are given. Frequency, I should point out, is in both equations. And so that is your bridge. If you're trying to solve for energy, but I give you wavelengths, then you're going to have to solve for frequency first and then plug it into the second equation. And then I could ask you to solve for wavelength or energy as needed as well. And again, units, I would like you to get in the habit of trying to use units, but I think for right now, we're focused on getting through these calculations. These are the first calculations that you're doing in chemistry. I want to make sure that we're doing okay with calculator work and scientific notation. So if you feel good about units, you should put them. Again, the one thing I will remind you of, I mentioned earlier, wavelength is very often given to you in nanometers. And we're going to have to convert that. So I'm going to show you a couple of example problems here. I'm going to have to switch screens. And when I do that example problem, we'll talk about how to convert nanometers to meters. All right, so I'm going to go ahead and switch over to a new screen here so I can show you a couple of practice problems. Okay, so let's look at this first example. They are asking us to calculate the wavelength of light that has a frequency of 1.5 times 10 to the 15th hertz. And so we've got the option of these two equations down here. And they're asking us for wavelength. And if you notice, there's only one of the equations that involves wavelength. So we're going to go ahead and use this equation to start, and frequency is part of this equation. So obviously we will just use this one equation to solve this one. And so first thing is let's rearrange this equation so that wavelength is our unknown, and that is equivalent to the speed of light divided by frequency. And so this is going to be pretty simple. We will plug in the speed of light. And divide that by the frequency that is given to us. And really the only issue here is you just got to make sure that you are plugging this correctly into your calculator. So hopefully you have watched and seen the notes on how to do that. And if you do plug this into your calculator correctly, you should get an answer of 2 times 10 to the negative 7th meters. And as we look at that, I know that seems like a really small number, and it is, but this is absolutely possible when it comes to wavelengths. And so you'll get used to that as you work through some of these calculations. So relatively straightforward. We just needed the one equation, and we've got our final answer for the wavelength. Okay, let's look at another example here. So we want to calculate the energy. And so down here in our equations, this is our unknown, and it's a photon with a wavelength 645 nanometers. And so wavelength is given to us right here, but we are trying to solve for something in this second equation. And so as we look at that, we're going to need to use both equations. And just as a heads up, this is similar to what you'll be doing in the lab. And so we're going to focus on this first equation right here. We're going to utilize the speed of light and the wavelength to solve for frequency, and you will notice that frequency is a part of both equations. So that's our bridge to get from the first equation to the second equation. And so as I look at this equation here, we're going to rearrange that. And so in order to solve for frequency, speed of light will divide by that wavelength that's given to us. And so in order to solve this, we'll have our speed of light on top. And even before I go any further, you'll notice that meters is our unit on top. And also, as we think through, wavelength should be in meters, as we see down here. Now, when you look at what was given to us, we are in nanometers. So we're going to have to convert. And conversions are going to be a large part of what we do in chemistry. Some of the simple math that we just kind of have to get used to is going to be unit conversions by dimensional analysis. And I know that sounds fancy, but really we're converting things. And so let me start with this. We want to convert nanometers to meters, but let's start here. If I told you you had 6 quarters, how many dollars do you have? And hopefully you think it through and you have 1.5, so $1.50. You just did dimensional analysis. Now, you didn't necessarily think through it this way I'm going to show you, but you thought through and said, okay, well, 6 quarters. What do I know about quarters and dollars? And so what I typically do here for conversions is what I call the train track method. And we want to convert from one unit to another, but we need a relationship. And so this box right here, I need to plug in a true relationship that I know about quarters and dollars. Now I know that 4 quarters equals $1. It's pretty straightforward, but one of the big things is that I want to convert the units, which means I need to get rid of the original unit, which is quarters. So I'm going to put 4 quarters down below, equivalent to $1 above. And you'll notice that when I do the math, I'm going to multiply across the top and get a number, and I'll multiply across the bottom. And again, there's only one thing on the bottom anyway. But as I do this, quarters will cancel out. So 6 times 1 on top is $6, and on the bottom is a 4 without units. So $6 divided by 4 is your $1.5. And so we're going to approach conversions similarly. And in this case, we've got meters and nanometers. Now, there are multiple ways to do this. You do not have to do my little train track thing. We will be doing that officially in later units. But at this point, if you can convert from nanometers to meters a different way, then by all means do that. I'm just showing you kind of this way because we will be using this a lot eventually. All right, so let's use the same approach of quarters and dollars, but let's get from nanometers to meters. So I'm going to plug in my number and unit to start. And I need a relationship between meters and nanometers. Now, you may not know that off the top of your head, which is totally acceptable. But what I will tell you is that 1 nanometer, and again, I'm putting nanometers on the bottom because we want to get rid of that unit and convert it into meters. 1 nanometer is equivalent to 1 times 10 to the negative 9 meters. And we're going to multiply across the top, multiply across the bottom, get our answer. You'll notice that nanometers will be over each other and cancel out. And so ultimately, when I complete this, and again, I'm just going to plug that in here. When I complete that calculation of multiplying across the top and dividing by the bottom, I will finally arrive at 6.45 times 10 to the negative 7, and we are now, 7, and we are now in meters. So now we can finally solve for this frequency. Be careful plugging this into your calculator. So again, this number right here times 10 to the negative 7 came from simply completing that math. So now I've got my frequency, and we said a long time ago that we were going to use this equation for the second part of this. And I know that energy is equivalent to Planck's constant, which I'm just going to copy. It's right here. And we will multiply that by the frequency up here. And we simply need to plug that into our calculator. Again, be careful of using the E and scientific notation. But when you plug this in, you should get a number. And our unit is joules. So again, be prepared to do this type of calculation from the lab. You're going to have to estimate your nanometers based on an image I give you. And finally, I know that that number looks really small for joules, and it is. It's a very, very, very small number, but we are talking about a single photon is what we just calculated. So a single photon, that energy is what we calculated. So we'd expect a really small number for the amount of joules. So hopefully this was helpful. You will be doing this a few times for your lab, and just kind of follow along with this expectation, and I think you will be fine.